Last week we did conservation of mass, right? And you guys got a little bit lucky because we didn't do the whole Reynolds transport theorem derivation. I did that on Tuesday. However, today you're not so lucky because today we are going to do a bit of a derivation, okay, for this lecture. So what we're going to focus today is on the law of conservation of energy. And the law of conservation of energy tells us that for an isolated system, right, a system that has no interaction with its surroundings, energy is conserved. But then what happens when the system is not isolated? When the system is not isolated, we turn to the first law of thermodynamics. So if you're taking thermodynamics, or if you are planning on taking thermodynamics, you will learn that the first law of thermodynamics tells us that the rate of change of energy with respect to time in a system will be equal to the rate at which heat is transferred, okay? And the rate at which work is done, okay? Whether it's positive or negative sign really depends on your sign convention, and different fields use different sign conventions. So for this particular class, I'm gonna set my work rate to be negative if it's done into the system, right? And my heat transfer will be positive if it is transferred to the system. And there's a reason for that, and you'll see once we actually derive the equation that we're going to end up with what's called the energy equation in fluid mechanics. But for now, this is what you need to know, and this is what we call the first law of thermodynamics. Okay? First law of thermodynamics. There are other types of energy that I'm not considering here. I'm not considering any transfer through radiation. I'm not considering energy from magnetic waves and all that stuff. But for now, what we do need to know is that energy, or the change in energy in a system with respect to time, will be equal to heat and work. These dots are simply Newtonian notation. That just means it's the derivative with respect to time. So this would be dq over dt. But this q, I want to be careful. This is actually heat transfer. So let me just write it down so that we don't confuse ourselves. This is where thermo and fluids kind of like start to argue a little bit. We both use Q, but for different things. Now, the reason I prefer to use Q dot instead of dq over dt is so that you can familiarize yourself with heat transfer as a derivative, right? As a derivative with respect to time. We're never going to look at flow with respect to time, right? Because flow is already a derivative with respect to time. So heat transfer, right, that's a Q, and then work. Now, we haven't covered work in this class, but I would assume that from your previous physics classes, you would have seen or at least studied work. So we're going to look at all these terms today, and we're actually going to try to define some of these a little bit better so that we have a better idea on how to use them. So I'm going to start with my energy. If you've taken a physics class, if you've taken a thermal class, can you more or less tell me how energy is defined? You know what energy is?
Work done over time.
Well, this is work done over time.
Oh, okay.
So yes, this is a form of energy, that's correct. But whenever we're looking at energy on a system, so just at a specific point in time, at a specific location in space, what is the energy in a system? Typically, we can divide energy into different terms, okay? Now, you don't have to memorize these terms, but you'll notice that the more you work on your homework, the more you'll start to memorize them, even though you don't have to. So we can define energy as a measure of kinetic energy, right? I'm just going to write it here, kinetic energy. We can perhaps describe energy. Are there any other types of energy that you can recognize? Potential energy. That's good. Potential energy. So potential energy, you know, is the weight multiplied by the elevation of an object. That is the energy potential. And we can write down weight as mass times gravity, and z will be my elevation. Now, the reason I'm splitting out weight into mass and gravity, you'll see later, is because I want my mass terms to be obvious and evident. So potential energy. And finally, we have what's called internal energy. Now, internal energy is a measure of any energy that's already inside a system. You can think of things like the temperature, right? And I guess, yeah, temperature would be the best example of internal energy. Now, why do we care to define these terms in the way that we are defining them? Because we would like to come up with a relationship that can look at or visualize energy, not from the context of a system, but from the context of a control volume. So that's why I want to define my energy, and that's why I want to keep my energy terms to be in terms of mass. But we'll see why in a second. The heat transfer rate is not something that I want to cover in this class. Not just this lecture, in this class. You're going to take, well, if you're mechanical, you're going to take an entire course dedicated to calculating this heat transfer rate, right? That's heat transfer. So in this class, let's just assume, right, that heat transfer is given to us. Okay, so heat transfer is given to us. There is some exchange of heat between a system and its surrounding based on the temperature differentials, but we're not going to look at that exchange of heat for now because this is a fluids class. So we cannot turn it completely into a thermal class. However, work is a mechanical property, and work is something that we can define and that we should define, because in fluids, we care about the mechanical properties of fluids, and work is one such mechanical property. So can anybody explain to me what work is? Force times the distance, right? If you guys may recall, you define work as simply F dot D, where F is your force vector and D is your position or distance vector. Now that's great, but that's only work. In this case, we're looking at work rate because we're taking the derivative of that force times distance with respect to time. Now, we don't have to go into too many details of how to write down the work rate in vector form. However, if it does make it simpler for you to remember this, work is force times distance, at least dimensionally. And if you take the derivative with respect to time, I'm just going to write down in terms of units. Work is force times a length. But if you take the derivative of work with respect to time, you're taking your force times the length with respect to time. Is there any fluid property that you can come up with based on one or more of these dimensions? Velocity, right? We have length over time velocity. So the reason I want to do this is because we can actually define work in fluid mechanics as the dot product of the force vector and the velocity vector. Now remember, from my sign convention, I'm actually using negative if work is being done on the system. So I'm just going to write down negative if my force is being applied into my system. Okay. Now work rate, right, work over time, is simply minus the force vector times velocity vector. But in fluid mechanics, and you'll notice that when it comes to energies, we typically don't want to deal in terms of forces. We prefer to deal in terms of stresses. So not just a force, but a force distributed over an area. So we know that stress, right, is simply force over area, right? So we can define force as a stress times an area. However, we can only make that definition, right? The definition of stress equals F over A, or F equals stress times A. This definition really only applies if your stress and your force is equally distributed in an area. But we can't really assume that, and we can definitely not assume that in terms of thermodynamics, because for most cases, your force won't be equally distributed over an area. So of course, we can turn to differential analysis. You know that we can do differentiation. We can find perhaps the dF over a tiny, tiny, tiny area, expand it over an entire finite area, and what we get is that force, right, can actually be looked as the integral of stress evaluated over an area. And I think we've done several examples of differentiation this semester, so I don't think we need to go back to the same differentiation example again, but what I do want you to get from this is that force can be seen, right, as the integral of stress and area. Now, because we're dealing with vectors, we need to consider our forces and our stresses to be vectors. So what this gives me is a definition of work that relates my force to a stress vector. But of course, we are taking the dot product with the velocity vector, so our work rate term will simply be the integral of the dot product of the stress vector times the velocity vector evaluated over an area. Now, up to this point, I'm assuming, I'm hoping, right, that we all understand where all these terms are coming from. Yes?
Why are we integrating the volume?
Sorry?
Why are we integrating the volume?
That's velocity.
This is velocity.
Oh, velocity.
Yeah. So just as a general convention, when I talk about volume, I'm going to always write a little line here, okay? So this is velocity because work is simply dot product of force times velocity, okay? Good. So up to this point, I'm hoping that we can all understand where all these terms are coming from, even though if we may not know the specifics of the vector operations happening over here, we should still at least understand that work, right, is force times length over time, which is force times velocity. And force is stress times area. Therefore, work is stress times velocity times area. I'm evaluating it as an integral because I don't want to assume that the stress is equally distributed. But if it were, this integral could actually just go away, and we'd have work equals stress times velocity times area, and that's it. But for now, let's keep it in integral form. Now here's where we're going to perhaps move into newer territory. How do we define the stress vector? So stress is a vector, and what does that vector mean to us? A vector is a quantity that has a magnitude and what else? And a direction, right? So that means that stress has magnitude and direction. So if I were to look at a surface, let's say I have a horizontal surface, and I have a stress acting on this surface at this direction, I can pretty much break down my stress vector into two components, right? I can break it down into a component normal to my surface and a tangential or shear component to my surface. There's a name that we give to normal stress components. So when you have a stress that's force over an area that's acting normal to the surface, what do we call that? Pressure, right? So the normal component of my stress is simply my pressure. So I can say that my stress vector is equal to my pressure vector plus whatever the shear component of my stress is. I'm just going to write it as shear stress. I'm going to try to write it in index notation, okay? Why am I writing pressure times n hat? Does anybody know what n hat means? What does the hat mean, yeah? Normal, right? Yep. And what does the hat tell us? That is a unit vector, okay? Remember, well, I haven't told you, but I always tell my static students to always visualize vectors as products of scalars and directions. So my normal stress is a product of a scalar, that's the pressure, that's the magnitude, times a direction of the pressure. So this n hat is a unit vector normal to my area. And you'll see why this unit vector normal to my area is important in just a second. So what does this tell me about my work rate? By looking at these equations, my work rate can actually be negative, and I'm just going to divide my stress term into these two components. I have negative the integral of my pressure, that is my normal stress, dot BDA. And then I have plus, but we have a negative sign, so plus the integral of my shear stress. I'll just write stress or tau sub s. Shear stress dot B dA. I'm just going to apply, right, negative times a negative is a positive. Can we agree on that? Okay. And then negative plus times a positive is simply a negative. So this is essentially my work rate. Up to this point, are there any questions? No? Good. If there are questions, feel free to ask. Yeah?
Why didn't you just add the shear stress with the pressure over there
Where?
instead of with tau together with
Oh, in here in the integral?
Yeah.
I'm actually going to separate these two integrals because this term, we're not going to cover it in class. So I'm going to try to simplify and get rid of it as much as possible. So out of convenience and just convenience, okay?
But you can add it together, right?
Yeah.
Okay.
This is just the same as just integral of p n hat plus tau s dot BDA.
Oh, okay.
Yeah, it's all the same. I just separated these two terms and separated the integrals in the terms because I would like to focus on one and not the other. Because again, this is a fluid mechanics class, and I want to talk a lot about rigid body mechanics, but we can't really spend too much time on it, okay? And here's where the not too much time comes into play. I'm gonna define my shear stress, okay, as combination of shaft work and shear work. So I'm gonna take this component, the component that I'm trying to get rid of, and I'm going to define it as simply shaft work and shear work. Now, what do these terms mean? The reason I'm defining it in this simplified way is because we're not going to go into the details, right, of these terms, but I do want to explain at least what they mean. A shaft, you know what shaft is? So shaft work is work done by a shaft. In other words, any rotating component of your machine. This can be a pump, a turbine, a propeller, a fan. Any rotating component of your machine, and here I'm talking to you as future mechanical engineers, right? Any rotating component of your machine will cause a work that we call shaft work. But we also have shear work, and shear work is work that results when the boundaries of your control volume are moving. So if a boundary of your control volume is moving, it will exert a shear on the environment, and that's what we call shear work. I'm trying to simplify them in these two terms because we're not really going to focus too much on these two terms. Instead, I'm just going to define them as shaft work, any work done by propellers, shear work, any work done by the movement of the boundaries of your control volume. So given this somewhat convenient definition, right, I can now write my work rate term as my pressure term. Negative is plus my shaft work plus my shear work. So this is basically out of convenience because I really want to focus on the pressure term. I don't really want to focus on these two terms. Up to this point, it looks like we've used some general mechanics equations, and we've kind of written it in such a way that we can focus on what we want and perhaps move aside what we don't want. Now, let's talk about energy. This is all work, right? This entire section was just about this one term, but now let's actually talk about energy. So conservation of energy is a law that applies to a system. But in this class, or at least in these next, I guess in the following 2 weeks, we want to deal with control volume. So what's the difference between a system and control volume? Can anybody help me with that? What's the difference between a system and a control volume?
Control volume is focusing.
Yep. Thank you, Gabriel. Control volumes, right, focus on locations in space. Systems follow fluid particles, so follow fixed sets of mass. This is an equation that applies for a fixed set of mass, but I would like to apply it to a control volume, to a location in space. And the way I'm going to apply it is by using the Reynolds transport theorem. Last week, on the first video of the week, we derived the Reynolds transport theorem. And if you don't remember it, that's all right. We are going to review it. The Reynolds transport theorem tells me that the rate of change, the material rate of change of an extensive property of fluid with respect to time is equal to the change of that property inside the control volume. So I'm going to integrate it over or inside the control volume. So I have the change of that property, rho dV, where this eta represents the intensive property. So N is an extensive property. Eta is its corresponding intensive property. We'll talk more about what that means in a second. So the rate of change with respect to time of an extensive property on a fluid is equal to the change of the intensive property times density, so that's just mass, in the control volume, plus the flux, that is the movement of that intensive property through a control surface. And why did I apply, or why did I derive this Reynolds transport theorem last week? Because this Reynolds transport theorem, notice, allows me to relate a law that applies to a system and express it in terms of control volumes. Now let's talk a little bit about this eta and what this n means. So n, as a review, is an extensive property. And extensive properties are those that depend on mass. Eta is its corresponding intensive property. And these intensive properties are those that do not depend on mass. So how do we relate eta and n? Well, the intensive property is equal to the extensive property divided by mass. And hopefully, I hope that you now start to see why I wanted to express my energy as functions of mass. Because if we want to apply this Reynolds transport theorem to find a relationship for the first law of thermodynamics in control volume terms, we need to know what the extensive property and what the intensive property are. So let's do that. Let's apply the Reynolds transport theorem to the law of conservation of energy. We have the change of an extensive property with respect to time. In the law of conservation of energy, what is that extensive property? Energy, right? Change in energy with respect to time. So my extensive property, in this case, is my energy. Therefore, my intensive property is my energy over mass. So if we look at energy and we divide it by mass, we're going to get an intensive form of energy. Now that intensive form of energy is what we call the specific energy. In other words, energy divided by mass, we're going to call it the specific energy. So let's look at energy. Energy is kinetic energy, that's mass times velocity squared over 2. If we divide the kinetic energy by mass, what are we left with? Yep. Energy is potential energy, right? So mass times gravity times elevation. So if we divide potential energy by mass, we get gravity times elevation. If we divide internal energy by mass, we get specific internal energy. So this is what we call the specific energy. You may have seen it in physics. You're definitely going to see it in thermodynamics. Okay, so specific energy is energy divided by its mass. And in this case, this eta is my specific energy. So now I can apply the Reynolds transport theorem. And wherever you see the extensive property, you plug in your energy. Wherever you see the intensive property, you plug in your specific energy. So what does that tell me? The Reynolds transport theorem says that the change in energy with respect to time is equal to the change of specific energy through my control volume plus the flux of specific energy through my control surface. And this is what we call the energy equation. But I'm missing something. This is just the relationship between system and control volume. But from the law of conservation of energy, we also know that this is equal to heat transfer rate minus work rate. And this is my conservation of energy. The change in specific energy with respect to time plus the flux of specific energy through the control surface is equal to the difference between heat transfer and work rate. And remember that these positive and negative terms are simply sign convention. You can choose them as you please. In the end, the signs are gonna, work themselves out. Up to this point, right? We haven't started deriving yet. This is like the start. But up to this point, are there any questions? Is everybody good? Okay. Yeah.
Why is Q positive again? You said that
This-
it's positive one.
So for my sign convention, I'm setting it positive if heat is coming into the system, but I'm setting my work negative if work is being done on the system. And the only reason I'm doing that is so that in the end, my equation looks like the traditional energy equation that most textbooks use. That's all it is. In thermodynamics, you may see this as a positive term because they use different equations where, they just have different sign conventions. Okay. So now, I hope that we brought our mathematics hats because we are going to derive a simpler, less general, but definitely simpler and easier to use form of the energy equation. It is 5:31. I'm hoping that we can derive this simpler form in about 30 minutes so that we can have about 15 minutes to do some problems. Okay? So let's go ahead and start deriving our simple form of the energy equation. Now, it goes without saying, but I will need your help deriving this form because I would like for everybody to take part in the wonderful world of deriving equations. So let's see what we have. What do we have to start? We have the conservation of energy equation. So I'm just going to write it down. Plus flux equals Q minus work. So we have the general conservation of energy equation. I want to simplify it a little bit. First, let's look at the work rate term. We had already said that the work rate was equal to the pressure term and the shaft and shear terms. So I'm going to write it down here. My work rate is equal to my pressure terms and my shaft and shear terms. I will require a bit of your patience as I rewrite and rewrite and rewrite this long equation, but I hope that we can all at least follow along what we're doing here. Work rate term will be equal to the pressure term shaft term and shear term. Up to this point, is everybody okay with what I just did here? Okay, good. So we have the energy equation, but we're expressing our work in terms of pressure, shaft, and shear. Now here's something interesting. I mentioned to my static students and to you earlier to always visualize vectors as products of magnitudes times directions. You may recall that last week we defined the area vector as simply the magnitude of the area times a unit vector normal to the area. That was the area vector. Now, there's a reason why I would like to express this area vector in this way. Because now, notice that we have a unit vector that corresponds to pressure. And pressure is always normal to a surface. So this unit vector, which is normal to the surface, is normal to this area where I'm integrating. Therefore, I can say that the product of the unit vector and the little area is simply equal to my little area vector. So from here, I get this. And the reason I'm doing this is because now, and hopefully now you'll see why I wanted to separate pressure. Now I can express this integral in the same way that I'm expressing the flux integral. So this will make my life a little bit easier. So if we set that n hat dA is simply the area vector, what I get is this entire equation, but here in the integral term, I'll have the integral of, oops, there we go, p dot dA. Because now we are moving this vector, combining it with the area. So we still need to take the dot product of this vector and the velocity vector, but now the vector is actually the area vector. And then what happens? We have the integral over a control surface of something times v dot dA. We have the integral over the control surface of something times v dot dA. Could I mix them into the same integral? I think I can, because we're integrating over, the same area. And all that changes is the coefficient of that integral. So the reason I want to express my pressure term as simply in terms of an area vector instead of an area magnitude is because now I can bring this pressure integral into my flux integral. So what do I have? I have the change with respect to time of what's happening inside the control volume plus my flux. So I have negative this integral. I'm going to move it to the other side so that it's positive. And I get the integral of specific energy times density plus my pressure. Up to this point. Is everybody okay with what I'm doing here? So I'm expressing this integral in terms of the dA vector, and then I'm bringing it all the way, keep forgetting to add that vector sign. I'm bringing it all the way into my other integral, so that I can join these flux terms as part of the same vector. And all this will be equal to my heat transfer rate minus my shaft work minus my shear work. Thank you. Does this equation look easier? I don't think it looks easier to manage. I think it actually looks pretty much just as hard. And the point of this entire derivation is to make our equation a little bit easier. So let's do a couple of things. Let's factor out the density here. So if I'm going to factor out the density, I get density times specific energy plus pressure over density. Did that make the equation easier? It pretty much looks the same, pretty much. Not that much difference. Okay. How about we insert the specific energy terms? Remember, specific energy was simply v squared over 2 plus gz plus my internal energy. Let's insert these terms. Let's see if that makes our equation a little bit easier to handle. So I had my change with respect to time of my specific energy. That's v squared over 2 plus gz plus specific internal energy multiplied by density evaluated over the control volume plus my flux rate. I'm going to move my density to the other side just to make it a little bit easier to handle. I got my kinetic energy, specific kinetic energy, my specific potential energy, my specific internal energy, and I have my pressure term. All this multiplied by density and then the flux, the flow. Density and then V dot dA. And all this equals heat transfer minus shaft work minus shear work. Is the equation easier now? Looks bigger. Okay. But we can work with this. Don't worry. First, let's remember a couple of things. This is a fluid mechanics class. Not only that, this is an undergraduate fluid mechanics class. And the reason we're learning fluid mechanics, well, the reason you're taking it with me is because you want to learn, I hope. And the reason we're learning this specific material is so that we can apply it into the field of mechanical engineering. What things can mechanical engineers do? What applications can mechanical engineers use with fluid mechanics? What do mechanical engineers do? It's an honest question. I'm a civil engineer. So what do mechanical engineers do?
Make machines.
They make machines. Okay, good. So in the creation of machines, do we have to consider energy? We do, right? So because we're looking at this from the context of a mechanical engineer, when we're designing machinery, pumps, turbines, any system that may involve energy transfer, we're going to have usable energy, energy that we can capture and use, maybe add, apply. But we also have, I guess I'll call it unusable energy, right? Useless energy. Nah, that's strong. We have lost energy, right? Energy that is lost to a system. For example, friction. Any energy that is lost to a system through friction, we cannot gather it back and use it. I mean, there's people that can try to pick up the heat generated from the friction, but pretty much we can agree that friction is lost energy. So all these lost energies, I'm going to clump them into a variable that I'm going to call loss. So my loss is this unusable, right? This lost energy that I can't use. So if you look at this term, what do you think constitutes lost energy? So think of it in terms of what cannot be captured and used for mechanical purposes.
Shear.
Sorry?
Shear.
Yes and no. And this one's a little bit tricky because shear is, in most cases, shear will be lost energy, but shear can actually be used towards our benefit. So really good answer, but Not quite for this particular scenario. Any other ideas?
Internal energy, U.
Exactly. Internal energy is lost energy, right? And one more. In mechanical engineers, we focus on mechanical processes. Which one of these terms is not mechanical? Obviously, we mentioned internal energy. Which other term is not mechanical? It has nothing to do...
Easy.
What?
Easy. Potential.
Potential energy is mechanical. There we go. Heat transfer, right? Heat transfer is not mechanical. So I'm going to define this loss as my heat transfer rate and, like Jet said, my internal energy. In other words, these terms. So I get that my loss is equal to heat transfer rate, the partial change with respect to time of my internal energy, rho dV, and the flux of my internal energy. Good. From a mechanical engineering perspective, where we want to deal with mechanical processes, this is what's going to constitute my loss. Now, I don't want you to think that this was a bad example. It's actually a good example of what may constitute lost energy. But because we want to leave all the mechanical terms in here, I am leaving the shears here. But for most practical purposes, we can actually count this as a loss as well. But we'll talk about that later. So I'm defining this loss. These are the terms that in this fluids class, we will not study. I'm not clumping them into a variable because I want to, well, actually I am, because I want to get rid of them, but simply because you should know that these are the terms that we will not study. That's a bit of a lie. We will study them, but from a different perspective, from a more mechanical, applied perspective and less of a theoretical perspective, okay? So then what does my equation now look like? I have my integral, right? My change with respect to time of the specific energy inside the control volume, except for my internal energy, because I don't have that anymore. Plus the flux of my specific energy, except for my internal energy, because I don't have that anymore. Plus my losses, and all that should equal my shaft work and my shear work. A little bit more manageable. We're not quite there yet, but a little bit more manageable. We set everything that we cannot use for our purposes as loss. And then we have what's essentially a bit of a more manageable equation. In the field, energy, I think, is one of those concepts where mechanical and civil engineering kind of coincide, because we will use energy in the design of turbo machinery. And pumps are as much a mechanical application as they are a civil one. Just today, this morning, I was working on a pressurized wastewater system where we used the energy equation. And I like the project. I want to turn it into some homework for you, but maybe not for this semester. I'll do it for next semester. But what you need to know is that both mechanical and civil engineers will deal with conservation of energy. However, most of these systems, where we have pumps, where we have pipes, where we have flux of something being transported, so you can transport coolant through a reactor, you can transport water to a home. Even though they seem kind of different, they actually have a couple of similar properties. One of these properties is that the flow will most likely be steady, and the flow will most likely be uniform. Which means that when we are considering energy, when we're looking at the conservation of energy for any system, it's good to figure out or to investigate if this system can be treated as steady and uniform. Now, in this class following today, we are going to focus exclusively on steady and uniform systems, which are representative of what you will see when you graduate. What does steady mean? Do you remember that from week 3? Constant with respect to what? Time, that's correct. So steady means that the change of any property or property with respect to time is 0. What did uniform mean? Again, week 3.
average velocity?
Average velocity is a uniform value, yeah. And what is that? Uniform means constant with respect to what? A constant over a what? Over an area, right? So when we say that our flow is uniform, what we mean is that the change of a property across an area is 0. In other words, the property is the same over an area. And this is actually a very good assumption to make when you're dealing with pipe systems. Of course, we know that the velocity will be greater at the center of the pipe. However, when we're dealing with large systems, where we got thousands and thousands of feet of pipe, you'll notice that it's actually safe to assume that the velocity and other properties are pretty much constant over the cross-section. And here's where I like engineering, right? In engineering, we can make those assumptions. If we were researching, if we were trying to come up with some scientific equation, then we can't. But because we are engineers, we can make those reasonable assumptions. Now, if my flow is steady, right, and uniform, the shear work, that is the work that occurs from the movement of your control volume, should be 0, because if my flow is steady, then my control volume should not move. Okay? My control volume cannot move if I'm calling it a steady flow. So what that means is that for steady uniform flows, we will pretty much neglect any shear stress, because we will focus on static control volumes, stationary, not static, stationary control volumes. Okay? And now what does the equation look like? Because I think that if I apply these two assumptions, steady and uniform flow, this equation is going to take a much more manageable form or shape. Let's look at this. We got steady flow. Steady flow. What can we do with the change in volume? D over dt? 0, right? Okay, so steady flow. We can ignore the change of the specific energy inside the control volume. Good. We mentioned that if it's steady, we can also say that shear is 0. And now we look at this integral. B dot dA. If my properties are uniform, that means that they don't really change across an area. So if all of these are constant over an area, what can we do? Take them out of the integral, and then we end up with integral of dA. And what's the integral of dA? Just A, right? Good. So what I end up with is my flux, and my flux corresponds of my specific energy multiplied by density, velocity, and area. And again, if you don't remember where this is coming from, remember that we have density, we have velocity, and then we have integral of dA, which is just the area of my control surface. Now, I want to be careful here. Let's say that I'm looking at a pipe as my control volume. If my flow is steady and we have flow coming into the pipe, then we have to have something leaving the pipe. Is that correct? Because there's no change inside the pipe with respect to time. So I can express this flux. This is the net, right? I can split it up into what comes in and what goes out, right? Okay. So I'm going to have my flux coming in and my flux leaving. Now remember, these are still, even though we're getting rid of the vectors now because everything is steady, everything is uniform, everything is pretty, we still need to consider vector notation, right? If it comes into my control volume, it's negative. If it leaves my control volume, it's positive. So I'm going to have my positive term leaving my control volume, and my negative term will be the flux entering my control volume. Oops. I keep writing dA. I don't know why I keep forgetting to just write A. Okay. So I have my flux. I have my losses. Again, we're going to deal with all this later. And all that should be equal to my shaft work. Now, what is this shaft work? I mentioned that shaft work, right, was any work done by propellers, so anything that rotates. So think of it in terms of the machinery that you will most likely build and design when you graduate from the school. What does shaft do to my system? So Is shaft work a method for me to add energy, remove energy, or both? Both, right? Can you give me an example of a type of propeller or a type of rotating shaft that adds energy to my system? What? A fan, right? Another example? We have a more generic term for that. What? Adds energy, adds energy. You're close. Let's say I want to increase the energy of the water in my reservoir so it can be pumped into, I used the word already. So it's pumped. I should have thought about it. All right, so our shaft work can be whatever's added to the system, which I'll just call it my pump power. Okay? Negative, because we're using vector notation, where into the control volume is negative, out of the control volume is positive, so pump power. And then, Jibril, any rotating shaft that removes energy from my system? You said it earlier?
Is it a turbine?
Turbine, right?
Yeah.
So turbines capture energy from the system, right? Convert that kinetic energy into mechanical energy for use. So I'm going to call it my turbine power. Now, just because we call them pump and turbine doesn't mean that it has to be a pump, it has to be a turbine, right? We're just given these names to represent any shaft that adds energy and any shaft that removes energy. Is that correct? So I want to make that clear, right? The propeller of a ship adds energy to my system, right? So we can consider it pump power, even though it's not technically a pump, okay? So we're using these terms, pump and turbine, in order to represent energy added, energy removed. And of course, because it's the derivative of work with respect to time, we can call it power. So pump power, turbine power. It's still not quite the equation I want, okay? And what I'm going to do is I'm going to change the dimensions of this equation. And we'll learn why probably later today or perhaps next class. We'll learn why I want to change these dimensions. But let's think of, for example, flow in a pipe system. Earlier this class, as in several weeks ago, we learned of an instrument that we can use to measure pressures in the pipe. Do you remember what that instrument was? Manometer, right? And manometers allowed us to understand or to figure out the pressure in a system based on a depth of liquid. So essentially what we're looking at, and when we look at manometer, is we're expressing our pressure in dimensions of length, right? Simply a length of water or a length of a fluid. Now the reason we do this is because using length dimensions actually simplifies our processes. Because if we can express pressure in terms of length, we have pressure here, perhaps we can express everything else in terms of length. So what I want to do in this equation is I don't want to leave it this way. I would like to express it in dimensions of length. So let's see. How can we turn this equation, into dimensions of length? My advice is to pick perhaps a property that you already know, and then figure out how we can turn this property into a length.
Gravity.
Density.
Gravity.
All right, we're getting somewhere. We're getting somewhere. Let's pick the easiest term to study. Out of all these terms, which one's the easiest that you think can be converted into a length? Which one?
I think gravity.
Okay, there we go. Tamiya?
Yeah, because it's height.
Yeah. So what are the dimensions of z? Length, right? So perhaps let's figure out how we can leave this z alone. So I'm just going to look at this term individually. I have my term is gravity times elevation times density times velocity times area. So what do I have to divide all these terms to get only a length?
Gravity.
Gravity,
Density.
density.
Velocity and area.
Okay. So if I divide all of this by gravity, density, velocity, and area, you're saying that I get a length. Is that correct? Now, because of dimensional homogeneity, right? If I divide all of those terms by gravity, density, velocity, and area, I should get all of my terms expressed in lengths, right? Because the equation is dimensionally homogeneous. So that is what I would like to do. So I'm going to take all of my terms, and I'm going to divide them by gravity, density, velocity, and area. And what is this? Density, velocity, and area. We know that velocity and area is flow rate. And what is density times flow rate?
Flux.
Flux, right? That's correct. So I'm going to take all these terms and divide them by mass flux times gravity. And then what does my equation look like? Mass flux is density, velocity, and area, so all of these cancel out. Is that correct? Perhaps let me write it here. Mass flux is density, velocity, and area. And then I have my gravity. So we can say that these three terms cancel out. And I end up with my velocity squared over 2g plus, we get gravity times elevation over gravity. How much is that? Gz over g. Just z. Okay. Plus pressure divided by density times gravity. What's density times gravity? Specific weight. Good. So we have all these energy terms leaving the system minus the same terms entering the system plus my losses over mass flux times gravity equals, let's see, I got my pump power, so I'm just going to say my pump power divided by mass flux times gravity minus my turbine power divided by mass flux times gravity. Okay, good. We're getting somewhere. What are the dimensions of each of these terms? Length. Good. Let me make a couple more definitions to fix this. We can say that the energy expressed as a length is called head. That's just the name we give to energy expressed as length. In other words, we have kinetic head, potential head, pressure head. We have losses here. So I'm just going to call this the head loss. Okay, simply the losses expressed in terms of length. And because they're called head loss, I'm going to give them a variable of h sub L, which is simply equal to losses over mass flux times gravity. We have my pump power divided by mass flux g, which I'm going to call pump head. So pump head will be equal to pump power divided by mass flux times gravity. And then we have a turbine head, which will be equal to turbine power divided by mass flux times gravity. These are my head terms, okay? Which is simply energy expressed as a length. These two terms will be important for us, and we will actually use them in coming lessons when we look at pumps and turbines, which is, I guess, at the end of the semester. But expressing these terms in the energy equation and rearranging the equation a little bit. You'll see that for most textbooks, for most problems that you see, we're going to identify my inlet control surface with the number 1 and my outlet control surface with the number 2. I'm going to rearrange those terms a little bit. First off, I want to move this. I want all my terms to be positive, so I want to move all my in terms to the other side. And I'm going to express my in terms. And I'm going to move pressure first. So I got pressure. I have velocity. I have elevation. I want all my terms here to be positive, so I keep my pump head. And then I'm going to move everything else to the other side, so we have our exit terms. Again, pressure, velocity, elevation. I'm left with my losses and my turbine head. And this wonderful, simple, easy to use, length dimensionalized equation is what we call the energy equation. Ta-da! For steady uniform flow. Ta-da! In length terms. Ta-da! Energy equation. Any questions? Why do I put you through 1 hour of derivation to arrive at what I could have initially just given to you? Because I want you and I need you to know where all these terms are coming from, why we are expressing them the way we are. Notice that when you talk about energy, you normally don't include pressure, right? Energy is kinetic, potential, and internal. So where did my internal terms go? Well, my internal terms are part of my loss, okay? And why do we get this pressure term? Because this pressure term comes from my work. So my pressure terms and my pump and turbine heads are part of my work rates. My heat transfer rate and my internal energy are part of my head losses. So as long as you understand where all those terms went, you should be able to reconcile this equation with what you learned in your thermodynamics class. Of course, it would be selfish of me to spend the entire class deriving this equation, prepare a nice video for the internet, and not give you any engineering applications. So because we have a few minutes left, let's go ahead and try a simple problem.
I have a quick question. Now that
Yeah,
you-
sure, throw it at me.
Well, never mind. It just went away. Well, I was gonna ask you for the area right here with the dA. It's the cross-sectional area, right?
That's correct.
Okay.
Yeah. So when we're looking at any control volume, right, whatever control volume, right, that area should be equal to just the area of the control surface. So the area where things enter and or leave your control volume. Okay? That's a great question. When we're looking at a system in a pipe, what do you think the area should be? The cross-sectional area of the pipe. That's funny. Not funny, but it's one thing I like about this equation is that notice that we actually got rid of our area terms, right?
That's what I was
So this will allow us to pick any point in a control volume, set it as a control surface, without necessarily knowing the dimensions of that point. And that's actually going to be a big help for us. And you'll see why in this problem. Let's do... Yeah, let's do example 513 from the book. This is a good one. I'm going to start it over here. You know, sometimes I may forget that you are students with lives outside of this class, right? When I assign homework and prepare these extremely hard exams. But if it makes you feel better, I'm actually taking a fluids class, right, for my PhD at Tech. And it's like 100 times harder than this one. And the professor, just like me, thinks that I don't have a life, the same way that I think that you don't have a life. So what goes around comes around. So if you're ever studying at 1 a.m. on a Friday for the exam, hopefully it'll make you feel better that I'm also probably studying at 1 a.m. for an exam. So hopefully that will give you a little bit of motivation when you're preparing for the second exam, which will be an interesting, very interesting exam. So example 513, we're given this interesting system where we have an irrigation pump that supplies water to a pond. So my system starts at a lower pond. We're going to call it 1. I should not have done that because I wanted to ask you what's my inlet, what's my outlet, but never mind. A lower pond that I'm going to call 1. And this pond is connected via a hose to a pump that transfers, that transfers flow into another pump. Okay. Water surface, water surface. You want a prettier picture? You have one in your book. Okay, we're given some dimensions, right? We're told that we have about 7 feet of piping, about 8 feet of piping in the vertical direction. What else do we have? We're told that the rate at which water is being transferred from the lower pond to the upper pond is at 2 cubic feet per second. And we're told that the pipe has a diameter of 6 inches. Okay. Assuming that the head loss is a function of a length of pipe. In other words, assuming that my head loss is 0.1 foot per foot, and this is head loss due to friction, then what is the horsepower required by this pump? Ooh, horsepower. We haven't said that word in the entire class. Whatever will we do? First off, when we're asked for power, your mind should go to energy. Yes?
How can you have any head power when it's going up in elevation by a pump?
Sorry?
Like your head force coming from pond 1 to pond 2, but you're going up in elevation.
Mm-hmm.
How can you have a head force on that?
Well, you have a pump, right?
Okay.
The pump adds energy to the system. So, and here's one important thing about any system when we're dealing with energy. Don't think of this as one pond, a pipe, a pump, and a pond in that order. We're studying a control volume, right? We're studying a control volume that starts here, ends here, but what happens inside the control volume is not our concern. Because remember, when we're studying control volume, anything that happens inside the control volume was handled by that integral, right? Integral of eta rho dv. But we already canceled out that integral, right, in this derivation, which means that we don't care about stuff happening inside the control volume. We are only caring right now about what enters and what leaves, what is added, what is removed. If it makes it feel a little bit better about it, you can visualize your pump as being here and simply pushing water upwards. You'll notice that in the future it doesn't really matter because the pump, all it does is create a pressure differential, and as long as these two systems are connected, the pressure differential will move the water. Okay. But yeah, if it makes it feel better, if it makes it feel a little bit clearer, visualize the pump as being down here. Okay. So we're asked to compute horsepower. Have about 5 minutes left in class. How do you think we can compute this horsepower? Like, what can we do? We have a system. We're asked for horsepower. Do you think the energy equation may apply here? Of course, otherwise why would I waste your time in this class, right? So let's write down the energy equation first. That's what I would do if I were you. I would write down the energy equation first, and then I would try to figure out what are the terms in this energy equation. So a couple of things to remember. The energy equation is an equation evaluated over a control volume, okay? Which means that we need to have a control surface that enters the volume, where fluid enters the volume, and a control surface where fluid leaves the volume. So here is how I would approach this problem. I have my energy equation there, and I'm going to look at those terms, and I'm going to think, do these terms matter for this computation? I always like to start with my pumps and turbines. First off, is there a pump in this system? Okay, so this matters. Okay. But is there a turbine in this system? Okay, good. So we simplified our energy equation. We removed one term. Good. If we look at my inlet and outlet terms, in this control volume, where would you place your inlet control surface and where would you place your outlet control surface? So in this entire diagram, where does your control volume start and where does it end? All right, starts at the bottom, ends at the top, but then where exactly here?
Start of the hose
You're saying start of the hose? Okay. And then where would it end?
to the pump.
Okay. Now I have a suggestion. Whenever you figure out where to set your control surface, always pick whatever makes it easier for you to drop some of these terms. Remember I told Cole that this is a control volume and we can look at it as a whole without caring what goes first, what goes later. So what I will do, because I'm looking at this system as a whole, I'm going to set the start of my control volume at the water surface. And you'll see why in a second. I'm going to end my control volume at the water surface. So my control volume starts at the water surface. So if you're a particle, you can imagine yourself moving from the water surface all the way down through and then ending up at the water surface again. Now why am I doing that? What's the pressure at the surface of water?
0.
Okay. What's the pressure at the surface of the other water? Okay. So atmospheric cancels out. Good.
So if we were to start in the pipe, we have to know how deep the pipe was.
That's correct. And then your pressure will be just gamma H.
Problems like that in this class?
Sure. I can do one for the test. Thank you for recommending.
No, I'm not.
No, so for the most part, I'm not going to tell you where you want to where you're going to set your control volume. That will be your choice as an engineer to make. And if it were me, I would always select my surface because I can always cancel out my pressure. Now think of velocity, and this is interesting. What's the velocity of this control surface?
0.
Why?
It's standing water.
Yep. Technically, right, if we want to be as precise as can be, it is moving, but at what rate? You go to Lake Lanier, right? Lake Lanier, water is always flowing out of that dam, but does the water surface elevation change at any rate that you can see? No. So we can take the velocity to tend towards 0 at the surface of water. Does that make sense for everyone? Daniel, are you good? Okay. And now, what do I have? I end up with a simple form of the energy equation where I have my elevation, my pump head, my elevation, and my losses. Got 3 more minutes. I think we can finish this this term. What was the point of this exercise? What are we looking for? Horsepower, right? So which of these 4 terms may include the horsepower within it? HP, right? Pump head. Okay, so let's say that I want to solve for pump head first. I get pump head equals to the change in elevation plus my head losses. Do we know the change in elevation? Yep. Yeah, it looks like it's going to be 8 feet. Good. And finally, we get our head loss. Now, we're told, and this is actually kind of strange because normally we don't get head losses in terms of length or as a function of length. We typically get head losses as functions of other properties of the pipe. But for now, we're just told that for every 1.1 foot of pipe, or sorry, for every foot of pipe, we will have 0.1 feet of head loss. Okay? So, and I'm just going to cheat a little bit here. I'm just going to tell you what we're being asked to do. All we're being asked to do is to find the length at which the flow in this system is experiencing friction and multiply it by 0.1. That's all we're doing. Okay? So what is the length through which this flow or this system is experiencing friction?
7 feet plus 8.
Okay, so 7 plus 8, right? Because flow really experiences friction at the pipe only. Any friction that occurs from the sides of the channel is negligible because the velocity of flow in the channel is negligible. Okay? And again, this was a little bit of a cheat here because we normally don't deal with losses in these terms. So I'm just going to say 8 plus 7, is that 15? Okay, so 15 feet multiplied by my factor of 0.1. Okay? And all that is equal to the pump head. This means that the pump head is equal to 8 feet plus 1.5 feet. Now, here is where I am going to differ from the book. Now, I don't like normally to say your book has errors, but there is one here. Okay? So, in the book, what we're selecting is we're selecting our outlet to be at the outlet of the pipe where flow does have a velocity. Okay? Now, I have problems with that selection. Okay? The first thing is that while we could assume atmospheric pressure, that is not always the case. In things like wastewater engineering, yes, that will be the case. You design your pipes to have a pressure of 0 at the outlet, but that's not the case for every pumping and piping situation. So what I'm going to do is I'm going to choose my point at the surface, differing from the book. There's 3 problems where I differ from this book: a stability problem, this problem, and another pump problem. Okay, so I'm differing from the book by selecting my point at the surface. Okay. Now, the reason I'm mentioning that is because if you do look at your book, you may see that the answer is slightly different, and it's because of that, because of where we chose our points. But I believe in myself. Okay. So we get 8 plus 1.5. We got 9.5 feet, and that's the pump head. I promise you we're going to leave now because it's time to go. But How do we go from pump head to horsepower? Remember that pump head was equal to the pump power, so horsepower, divided by mass flux times gravity. Do you have pump head? Yes. You have flow rate, so can you calculate this mass flux if you have the flow rate? And you have gravity? So you can go ahead and solve for horsepower, and I will let you take care of that yourself. Okay? I'll see you next week.